Hey, what's going on, guys? So today we are going to present about spatial temporal prediction of ambient PM2.5 using satellite imagery. Let me explain a few words before we continue. So spatial is related with locations and temporal is associated with time. Prediction means forecasting and ambient means neighborhood or surrounding. So PM2.5, air pollution. PM2.5 is particulate matter 2.5. It's a pollutant, and these are just small particles in the atmosphere that are 2.5 micrometer or less. These particles, our eyes cannot see them, they're too small, but they can infiltrate our bodies and cause harm. So the other thing is satellite imagery. These are images that are captured by geo-orbiting satellites that move around the Earth. So yeah, so we are trying to predict the surrounding PM2.5 using those images. But to give you context, we need also ground truth measurements which are on ground so that to validate our predictions. So yeah, so we reviewed some literature and specifically this one we are presenting. This study uses graph neural networks to forecast PM2.5, but they also introduce a challenge of a technical challenge of distribution shift. So distribution shift is just the changes in the distribution of data uh, over a long period of time. So these are the keywords, but I've already explained most of them. But I reiterate that distribution shift refers to the changes in the underlying distribution of data over time. And these changes actually affect the performance of the models that we develop. So you can use graph-based approaches, deep learning approaches, or non-graph-based, like this study specifies. But the computational problem in this study is actually this distribution shift, the changes in the distribution of the data over time. For example, ERCO has been putting up many devices. They keep changing, and the distribution of data keeps changing over time because this data actually depends on time and location. So this one is a challenge, and it's the computational problem or the computational challenge in this study. I'll call upon my friend Elijah to do the rest of.
Hey, thank you, Peter. The authors looked at the several variations of the GNN models that were developed. One was the graph convolution networks, then the spatial temporal graph convolution networks, and the attention-based spatial temporal graph convolution networks. These performed well in scenarios without distribution shifts, but struggled more with shifts. Picking the author's mind, the authors thought the spatial temporal GNNs perform well on spatial temporal data, but they also asked questions like how do they fare against distribution shifts? About the dataset they used, there were 534 monitoring stations and 5 features were extracted. As you can see them, the PM2.5 temperature, humidity, wind, and plus the location, which is the latitude and longitude. So the graphs that you see there show different correlation for the sites. The first one shows the geographical proximity between the sites, and the other one shows the correlation values between the sites. Um, their models were evaluated using the root mean square error, which we have all studied. And we'll just go and show you the EDA that we did on the data set that we got from the AECO.
Yeah, so to use satellite data, it has to be validated with ground truth, as I've already said. So we got airco data. Airco is a project that monitors air quality across Africa. So we got their data across the devices in Kampala, list of the devices from Kampala between 2020 and 2022. So all the data they collected there, and they have different features there. So we did EDO on this as we extract our satellite data that we shall present in the next presentation.
Yeah, so the EDA that we did, as you can see, the parameters that we have, The so you can go on and then we present the trend analysis that showing the different trends. Um, then the data averages for both pollutants, as you can see the graph here, uh, you can see the data average PM2.5 and the PM10. The PM2.5 is represented by the blue, and then PM10 you can show them just a little. No, you can. The PM2.5 is represented by the blue, and then the PM10 is represented by red. So as you can see, like at the beginning of the month, the year, the first months, the the clouds, the skies are clear, and more pollution is registered. Uh,
At the beginning of the year, so we also did monthly averages, and you can see just monthly average for both pollutants. The represented PM10 is the red and PM2.5 is the blue one. And besides the trend analysis, we also did spatial analysis. I've already said that spatial is associated with locations, and then we just got the averages of the average of the entire data to generalize if that place, a specific place, was safe or not safe. These are markers on this map, and if I'm to hover at one of them, you can see that Bugolovi Nakawa, this green one, was actually safe generally for the 2 years. And this place, which is Luzira, it was averagely safe, but place like this one, Rubaga, it was actually not safe based on the P2, PM2.5 reading that we got from the device. Now, besides the spatial analysis, we also did comparative analysis, and here we just compare the raw value and the calibrated value. We want to see, and the trend is almost the same, apart from here where it's a bit different, but the trend is actually the same, just showing that when we use the calibrated value to convert the raw value, when you use the calibration to convert the low value to the calibrated value, it's all the same, like it's uniform, apart from this and this. So we did that for this is PM2.5, and we did that for the other pollutant, which is PM10. So PM10 are just particles that are 10 micrometer or less. And we also did data quality assessment. So we try to find out how good this data is for this task. And we investigate missing values and a few other things. And we drew a report here. We know that some features have missing values. Then others have some outliers, what we call outliers here. But and some have negative values where they're not supposed to be. So we need to correct all this before we can continue to use this data. We also drew, this is a heat map. It shows the relationship, the correlation between different features. So we want to know how the other features related to the PM2.5 calibrated value, which is our target variable. And yes, besides that, we want to do, of course, fill in missing data before we come back to this heat map. We want to fill in these missing values, and of course, we tried out a few things like the forward fill. The forward fill, the forward fill is a very basic. It's a very basic technique that we cannot consider here, but of course, we used it here. But what we're considering is to use LSTM imputation, because LSTM does very well on this time series data. So we shall use it to try and predict the missing values and then fill them in, and then later we can use the same LSTM to build a model for prediction for our values. We can also use we are also going to use this graph neural networks and put in, considering the distribution shift. So for now, we are still doing a lot of work down there, but we shall present that in the next presentation. And thank you.